Have you ever just stopped and wondered how the internet actually works? I mean, how you can be streaming a movie while someone else in your house is on a video call and millions of other people are doing their own thing, all at the same time through the same cables? Well, the secret is a concept so fundamental, you're literally using it this very second. So let's dive into the invisible magic that makes it all happen.
It really does seem impossible, right? How do all those separate streams of information, all that data, not just crash into each other in a massive digital pileup? That's the core question we're going to answer today.
And this image here just lays out the problem perfectly. On the left, you've got all this different stuff, a video stream, an email, your web browser, you name it. And on the right, just one single link, like a fiber optic cable. The entire challenge is getting everything from the left through that one narrow pipe to the other side.
And yeah, this challenge has a name. It's the digital traffic jam. And honestly, it's a problem we've been trying to solve since the very first communication networks were ever built.
And you know what? It's a problem that's only getting bigger. The more we connect, the more data we use, the more crowded that single link becomes. Without a system to manage all this, everything would just grind to a halt.
So, what is that system? Well, the hero of this story is a concept called multiplexing. It's the really elegant, clever solution to the whole digital traffic jam problem. In the simplest terms, it's the art and science of sharing. That's really all it is. It's how we take one big resource, that single data link, and make it possible for a whole bunch of signals to use it at the exact same time without interfering with each other.
Think of it like this. A multiplexer, or a MUX for short, is like the on-ramp manager that cleverly merges all the cars onto the highway. The single link is the highway itself. And then way at the other end, a demultiplexer, or a DEMUX, acts like the off-ramp, directing each car to its correct destination. So you combine, you transmit, and you separate. That's the core loop.
Okay, so how does this merging actually happen? Well, the first major technique is called frequency division multiplexing, or FDM. And as you can probably guess from the name, this is all about sharing by frequency.
And this visual illustrates the concept perfectly. With FDM, we're not trying to merge all the cars into one lane. Instead, we take our wide digital highway and we just paint lines on it, creating several smaller, dedicated lanes. Each signal gets its very own lane.
All right, let's get a little more technical. FDM is an analog technique, which means it deals with continuous signals, kind of like the smooth waves of a radio broadcast. It works by taking each signal and attaching it to a different carrier frequency. Think of this as assigning each car to its specific lane number. And to prevent these signals from drifting into each other's lanes, small empty spaces called guard bands are placed between them. Now, the crucial point is that lane is reserved for you, even if you're not sending any data at the moment.
And this visual shows it perfectly. See how time moves forward from left to right? But each channel stays locked into its own slice of the frequency spectrum. Channel 1 never mixes with Channel 2 because they are literally on different frequencies.
Okay, let's trace the process on this slide. On the left, you have 3 different signals. Each one gets combined with its own unique carrier wave. That's the modulation part that puts each signal into its own lane. Then they are all combined into one complex signal that contains all the original information, just perfectly separated and ready for travel.
You know, the best real-world example of this is just plain old broadcast radio. When you tune your car radio to 93.5 FM, you're telling your receiver to only listen to that specific frequency lane. Another station at 101.1 FM is broadcasting at the same time in its own lane and you don't hear them. All because of FDM. It's the exact same principle.
Okay, so now that you get the concept, let's see if we can apply it. Imagine you're a network engineer. You have 5 channels to multiplex. Each one needs a 100 kilohertz lane. And to be safe, you need a 10 kilohertz guard band between each lane. So, how wide does your total highway need to be? Think about it for a second.
Got an answer? The answer is 540 kilohertz. Did you get it right? Let's break down how we got there.
So here's the crucial part. For 5 channels, you only need 4 guard bands to go in between them. You don't need one on the very ends. So it's 5 times 100 for the channels, that's 500, plus 4 times 10 for the guard bands, which is 40. Add them up, and you get your total required bandwidth of 540 kilohertz.
So, frequency division is one brilliant way to solve the problem. But what if you can't create more lanes? What if you only have one? Well, that brings us to our next technique, time division multiplexing, or TDM. And this one is all about sharing by time. So instead of that multi-lane highway, imagine we're back to a single-lane road. How do you prevent a traffic jam?
Well, you have everyone take turns. TDM is a system where each signal gets to use the entire road, but only for a tiny, specific slice of time.
So here's how it works. Unlike FDM, this is a digital technique, meaning it deals with data broken into discrete pieces, like ones and zeros. It takes these digital signals and interleaves them. It just weaves them together one after the other. Each signal is assigned a repeating time slot. It might be user 1's turn, then user 2, then user 3, and then right back to user 1. And just like with FDM, that time slot is yours, even if you have nothing to send.
And this slide right here is the aha moment for TDM. Look at the data flow. A piece of data from source 4 goes, then 3, then 2, then 1. Then the cycle just repeats. 4, 3, 2, 1. Each user gets the full capacity of the link, but only for their designated microsecond. And this happens so incredibly fast that to you, the user, it feels like a continuous, uninterrupted connection. So let's put them side by side. FDM shares the frequency, TDM shares the time. FDM is an analog technique, TDM is a digital technique. FDM is like having your own dedicated lane on a highway. TDM is like everyone taking turns on a single lane road very, very quickly. Two different philosophies for solving the same problem.
When you step back and look at the big picture, these techniques aren't just clever engineering. No, they are a revolution in efficiency.
I mean, without these methods of sharing, every single phone call, video stream, or website would need its own dedicated physical wire running across the country and the world. It would be completely impossible. Multiplexing really is the invisible magic that makes our shared, connected digital lives possible.
So the crucial takeaway is this. At its heart, multiplexing is a philosophy of efficient sharing. It's about taking one large, valuable resource and dividing it up intelligently so that everyone can benefit. It's the reason our digital worlds can even exist. And that leaves us with a final thought. If we can use this principle to manage the flow of information so well, where else could we apply it? From our power grids to our roadways, what other systems could be revolutionized by the simple, elegant idea of taking turns or sharing lanes?